your first problem set submissions. At some point before you leave today, you should check the gradebook to make sure that that is reflected on what you think you had done. So if it got marked missing or incomplete, and you're like, hey, I think I had all of that in there, let's make sure that we have a conversation, you and I, before we leave, just to make sure. Or if I sent you an email because you sent me an email about something, that if you needed help doing something or getting it in the right spot, that we take care of that here before we go. Everybody cool?
Yeah.
Very good. Next thing is, today we're going to be looking at section 2.4. Just a little reminder of kind of where we've been and where we're trying to get to here in chapter 2. So we started chapter 2 by discussing a new unit of measurement for the angle. That was the radian. We discussed how to move back and forth between degrees and radians. In section 2, we reviewed our right triangle trigonometry, so how to do sine, cosine, tangent, etc. inside of a right triangle, basically SOHCAHTOA. In section 3, we defined a new way to draw angles so that we can draw an angle of any size, positive, negative, whatever. And here in section 4, we're going to do or complete our goal in chapter 2 that goal was to redefine sine, cosine, and tangent, etc., so that we can do them on angles of any size. So by the time we finish here in section 2.4, that will now be possible. Needless to say, section 2.4 is a pretty important section. It's one we will use over and over again throughout the rest of this semester. Everybody cool? All right, you ready to start? Okay. So let's start with, say, just some standard position angle. So again, standard position means that the initial side is on the positive x-axis and the terminal side rotates either clockwise or counterclockwise about the origin. So I'm going to call that angle alpha. Again, remember that in trigonometry, that little fish symbol is the Greek letter alpha. In trigonometry, we often will name our angle measures or our angles with the Greek letters because we'll have like variables for coordinates or side lengths and a bunch of others. It just helps, communicate what are we talking about here. So oftentimes Greek letters are representative of angles in trigonometry. That fishy symbol is the Greek letter alpha, like you remember from religion class when it's like, I am the alpha and the omega. Like the alpha is the first letter of the Greek alphabet, omega is the last letter. A lot of your Bibles written in Greek because the Middle East was all Greek colonies, or former Greek colonies anyways, from Alexander the Great when he tore through and busted up the Persian Empire. No. It's history, man. All right. So we have this angle, right? Angle alpha. I'm going to pick some point P on that angle alpha, and I'm just going to say the coordinates for P are just some generic x comma y. So I have some angle P or some angle alpha, and I've picked an arbitrary point P on that terminal side. Could be anywhere on the terminal side. I'm just going to give it the coordinates x comma y. Now, if I look at this, it seems to me that this kind of looks like a right triangle here. You guys see that?
Yeah.
Okay. What label should I give that side of my right triangle? Nope. Nope. Let me ask a different question then. So how do I plot, say, the point 2, 3? If you gave me directions on how to do that, what would you say? But directions, like if I'm the person going to draw it, like how would I know where to put it? You mean the other way around, though. Over 2, up 3, correct? So for me to get to this point P, how many did I go over?
2. 1.5.
I mean, look at the coordinate. I went X over, right? So what is this side? What label should I give that? Y. Everybody feel good as to why I named those? Makes sense. And this side, I'm going to call R. So I have this right triangle that I've drawn in green with sides X, Y, and R. What can I say about the relationship between those sides X, Y, and R in a right triangle? Gavin. Yeah, go.
What is the writing in the corner? What does that say?
Are you talking about alpha? That's that little fish symbol is the Greek letter alpha. Hey, we answered it. You don't have to like give him grief. I'm sure Gavin gets enough grief every day, right? You get your daily allotment of grief, I'm sure. All right. But what can we say about the relationship between the sides X, Y, and R in a right triangle? It's a right triangle. The sides in a right triangle, what can we say about them? Starts with a P. That's what we're looking for. We can say that R squared is equal to X squared plus Y squared, or R is equal to X squared plus, or square root of X squared plus Y squared. Can we cut the side conversations here, folks? Back corner again, I'm looking at you guys. Now, take a moment here. This side R is the hypotenuse for this green triangle, correct? In the red angle, what is R also? Well, there's no triangle for there to be a hypotenuse. So we're talking about the red angle. It's not a radius because there's no circle. It's the distance from the origin to the point P, right? Yep, right? And that distance from the point P to the origin, we could calculate just given the point, right? If I know where P is, I know the origin 0, 0, I can always use the distance formula to find that distance, right? So look at what we've done here for a moment. We've taken this right triangle and we've defined it using the coordinates X and Y of this point P, and this R, the distance from point P to the origin. So, for example, if I take, say, sine of alpha, normally we'd say that's opposite over hypotenuse, right? Well, we've just said that opposite is kind of the same as the y-coordinate, and hypotenuse is kind of the same as this r. Look at what we just did. We have redefined sine alpha. Instead of using sides in a right triangle, if it's y over r, that's the y-coordinate of this point on the terminal side over r, the distance from that point to the origin. None of that has to do with a right triangle. We can do that for the other five trig functions, and all of a sudden we have a new set of definitions for sine, cosine, tangent. And this is a typo. This is what we call our point definition for sine, cosine, and tangent. Because all we need to use this is a point on the terminal side of our angle. Is this definition something I would expect you to memorize? Yes. But here's the thing. Here's the good news. You already know it. This is just SOHCAHTOA, where opposite is replaced with y, adjacent is replaced with x, and hypotenuse replaced with r. So it's just SOHCAHTOA again. You just have to remember what letter opposite, adjacent, and hypotenuse is. Well, that's a pretty good news there, Mr. Kulik. I love it when, like, this new thing is really just this old thing relabeled.
Love that.
Right? Like, that makes my life easier if you're telling me I need to remember this. Heck yeah. So again, the pieces that we need how to find r. We need our point definition. And then probably our little translation back to SOHCAHTOA, right? Those are like the things that we'd be using going forward. All right, let's do an example using this new definition to do a problem. All right. Here it says the point -3, 4 lies on the terminal side of angle theta. Find the values of all 6 trig ratios for angle theta. Well, I'm going to start by just sketching myself a little picture because I'm still getting used to using my new definitions. So let's just make sure when we read this, we see the same picture. Is everybody okay with how I've drawn that? Just drew a standard position angle. Terminal side has to go through the point -3, 4. So just plotted -3, 4. Drew my line through it, and there's the terminal side of my angle. Everybody's happy? So the x value in this case is -3. The y is 4. And the r is square root of x squared plus y squared, right? That was one of our definitions that we pointed out before. Negative 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. And the square root of 25 is just 5. Everybody's okay there? So we have now x, y, and r. So I can say that sine theta is, according to my previous definition, or my new definition, I should say, y over r, so 4 over 5. Cosine theta is x over r, so negative 3 over 5. And tangent theta is y over x, so 4 over negative 3. Now remember, cosecant theta is the reciprocal of sine, right? So I can just write 5 over 4. I don't have to go back to that other definition. I can just still use these reciprocal rules here. So secant is negative 5/3, and then cotangent is negative 3/4. That was pretty quick and easy, right? It's not too bad. Just had to figure out what r was and then plug us stuff into our new formulas. Screw, like I can do that. Yes, sir. What do we notice about the values of sine, cosine, tangent, etc. that happened here that we've never seen happen before? Look at the values. What has happened here that we've never seen happen before? We have some negative values. Yeah. That's not happened to us before, right? We've never seen sine or cosine be a negative number before. That can happen now. And in fact, it's predictable when it's going to happen based on where the terminal side of our angle is. Let's do a little work to kind of suss that out. So we're going to be looking at making predictions, being able to figure out where sine, cosine, etc. is either negative or positive. So I'm just going to kind of draw a picture to help us kind of organize this information. So I'm just going to start with the xy axis. And I'm going to start in quadrant 1. In quadrant 1, the x coordinates are positive or negative? Positive. And the y coordinates are positive. And then remember, r is a distance. That's always positive. So all of our trig functions should be positive in the first quadrant because they're all involved x, y, or r, correct? So sine theta, cosine theta, tangent theta, cosecant theta, secant theta, cotangent theta are all greater than 0. So I'm going to say all, and I'm going to write an A there for all because all of our trig functions are positive. I'm going to track what stuff is positive in each quadrant. That's what the letter I'm going to write there is going to tell me is what stuff is positive in that quadrant. If I look at quadrant 2, x is positive or negative? Negative. Y is positive. So anything with an x in it is going to be negative, right? So cosine, secant, tangent, cotangent, all of those are negative. And sine and its reciprocal are positive. So I'm going to put an S here for sine and its reciprocal being positive. I'm just going to track what's positive in each quadrant with a one-letter abbreviation. Right? I know if a number is positive, then its reciprocal also has to be positive, because all I'm doing is like writing 1 over the number, right? In quadrant 3, x is positive or negative? Y is good. So anything that involves just one of x or y is negative, but anything that involves both of them is going to be positive, right? Because negative over negative is positive. So I know that sine, cosine, cosecant, and secant are all negative, but tangent and its reciprocal, cotangent, are all positive. So I'm going to write a T there for tangent and its reciprocal being positive. So far, so good? Because tangent and cotangent involve like y over x or x over y, and negative over negative is positive, right? So those will be the only positive ones there. Yes?
So what are the other than sine, cosine, what are the other ones?
Cosecant, secant, cotangent.
Yeah.
Those are the other three.
So those just different
They're just reciprocals of the. They're just reciprocals of those three, right?
Oh, so
Sine and cosecant are reciprocals. Cosine and secant are reciprocals. Tangent and cotangent are reciprocals.
oh, okay.
So anything that's true for sine would be true for cosecant.
Oh.
Anything that's true for cosine would be true for secant. Anything true for tangent would be true for cotangent, because they are reciprocals of one another. Is that okay? Mm-hmm. And now quadrant 4. X is? Yeah, it's positive, and then y is negative. So anything with a y coordinate is going to be negative. So that's sine, tangent, cosecant, and cotangent. But cosine and, oops, those are negative. But cosine and secant are positive. So I'm going to put a C there for cosine. So the way that I remember that, well, the way that they taught me back when I was your age, is we use the mnemonic all silly turtles crawl. What? Where the A in all stood for the all. The S in the silly stood for sine. The T in the turtles stood for tangent. And the C stood for the cosine. You can make up your own or your own mnemonic if you'd like. Okay? But this skill of being able to tell what quadrant something's in based on if it's positive or negative, or being able to tell if something's positive or negative based on the quadrant. That's a really important skill that will not go away. It will be an important skill for the remainder of the semester. So this also something we should basically have memorized. Okay? Let's do another example. Now that we took that little digression to talk about positives and negatives. The next example says defines cosine of 150. Can we do that using SOHCAHTOA?
I don't know.
No,
I didn't know how to do it.
because 150, you can't have a right triangle with a 150-degree angle in it. So we can't do SOHCAHTOA on this, right? So we're going to have to use our new definitions, our point definition for sine, cosine, and tangent. So I'm going to start by drawing a picture of a 150-degree angle. So I've drawn my x-axis. I'll draw my initial side on the positive x-axis. To go 150 degrees, 90 degrees gets me through the first quadrant, and then like 60 more. And since that part of the 150 is 60 degrees, what's the part underneath that angle? It's got to be 30 degrees, right? Is everybody clear as to why that has to be 30 degrees? We're good? Okay. I'm going to pick some point P on that terminal side, and I'm going to draw myself a right triangle. Is everybody okay there? So I have a right triangle with one 30-degree angle in it. What's the other angle have to be? It's got to be 60, right? And what does that mean we have here? A 30, 60, 90 triangle. Hey, I know the ratio of side lengths for a 30, 60, 90 triangle. So they would be A root 3, and 2A, right? Everybody's okay there? So what does the x-coordinate for P have to be? What does the x-coordinate for point P have to be? So let's go back and look at what we did in the very beginning. So the x-coordinate for point P was that side of our triangle, right? The left and right direction. So if we go down here, what does our x-coordinate for point P have to be? The left and right, right? Because we go over and then up. This is important now. But guess what? It's not quite right. Will, What is wrong with what we've written here? Just hang on. Hang on. I'm doing this way for a reason. Just hang with me, okay? Will, you said something earlier when I asked what the x-coordinate was that's right on.
No, negative positive.
Yes. Will is recognized because the terminal side of our angle is in the second quadrant. The x-coordinate must be negative. So this should be negative a root 3. That's the correct answer. That's why I said we're almost, and asked you to hang on with me because we're going to get to what's going on. Now, I will predict the next time you guys do this, at least 2/3 of you will forget that negative sign. I'm going to stop here and re-emphasize this, so maybe an extra 1 or 2 or 3 you guys remember. This is difficult, though, what I'm asking you to do, because we're using a geometric reason to put that negative sign in there. And that's tough. But that's the point of us drawing the picture. Without the picture, it's very unlikely you would remember that negative sign. Okay? Gotta draw the picture. We need those pictures. Okay. What is the y-coordinate for P going to be? So when we plot a point, we go left or right, and we go up or down. Which side is the up or down? It's A, right? So what does 2A have to be then? That's our R. The distance between the point P and the origin. So I know that x is negative a root 3, y is a, and r is 2a. So if I do cosine of 150, that is just x over r, which simplifies down to negative root 3 over 2. Again, the skill that we're doing right now of using our different definitions of sine, cosine, and tangent does not go away after chapter 2. We're going to see this over and over and over again in first semester. It is a fundamental skill that we need to make sure that we acquire right now in chapter 2. And we need to learn it in such a way that it doesn't fade the day after the test, that it sticks around, because we're going to be doing this over and over and over again. It'll be a normal step in future problems. Okay? Just trying to put some perspective on you as to, like, when you do these homeworks, you got to really do them. Okay? Do them so you remember. It'll make your life in the future much, much easier if we do a good job right now. This course is very much like kind of the same stuff over and over again with like a different name to it. And if you're good from the beginning, pretty smooth sailing. If you fight in the beginning about like how really well do I need to learn this, you're going to be fighting all semester about it. Okay? So you want to do this good and do this now. Okay. So there's one little thing left here, though. Along this process, there's one thing that we had a choice of that we could do different every single time. Each one of us could do this differently. Where did we make a choice when doing this problem that could have been different? It was where we chose to put P, right? P could be anywhere on that terminal side. We had our choice as to where to put it, right? This could get a little bit nicer if we standardize that choice. If we choose P the same way every single time. That's going to be the final piece to this puzzle. So the way we're going to do this is from now on, or I'm sorry, well, if we choose to do this, to simplify things, what we can do is we can choose our P always so that it's 1 unit from P to the origin. Okay? Now let's say we do that, and we take all the P's that are 1 unit from the origin from every single angle possible, and we plot those P. What shape is it going to make? Yeah. So we're choosing, we have any angle possible, right? So every single angle possible. We're going to pick P so that it's 1 unit from the origin on every single one of those angles and plot every single one of those P's. And we get a circle. That's right. Now, this specific circle, we're going to give a name. We call this a unit circle because the radius for this circle is exactly 1 unit in length. Everybody's okay with that? Because the radius is 1 on that circle. Okay. Now, in this class, when we talk about the unit circle as opposed to a unit circle, the unit circle that we're talking about is this guy right here. I'll give you a paper of this printed out next time we meet, okay? But until then, you have it digitally in the content library on your OneNote. But I'll give you a physical piece of paper next time. What this unit circle is, it's every angle that we can find an exact value on with what we know so far recorded in one place. So remember when we did cosine of 150 before, right? We drew that 150 degree angle. We made a little right triangle. That little right triangle is a 30, 60, 90. And using that little right triangle, we could say that cosine was, oh shoot, I forgot to do something. Let's pause here for a second. Pause for a second, I'm sorry. I got ahead of myself. Okay. So we had our point definition for sine, cosine, tangent, etc., right? Yes. Yes. And we're going to say, okay, we're standardizing how we're choosing our p so that the r is always 1. What is sine of y over r going to change to if r is always equal to 1? Becomes y over 1, or just y. So that gives us this, which is our third definition for sine, cosine, and tangent. That's our unit circle definition. Notice it's the exact same as the point definition, except r is 1 now. It's the only difference, right? It's the same definition, just r is 1. So sine of y over r becomes just sine of y. Cosine of x over r becomes cosine, etc., right? Is everybody okay so far? Okay. Now if I go back to this picture, again, this is just recording all of the situations where we can find exact values. So remember when we did cosine of 150 before, we drew the 150-degree angle, we made the little right triangle, we found the side lengths of it, or found the x, y, and r, and we concluded that cosine of 150 was negative root 3 over 2. This picture tells me the same thing. The way I use this picture is I locate 150 degrees. And then if I'm looking for cosine of 150 degrees, my definition for cosine is x. So cosine of 150 is negative root 3 over 2. Done. Nothing more for me to do. This is literally just a shortcut to doing a process that we could do by hand, but we don't want to. Okay, these come up over and over and over again. It's basically just a table of values, but it's written as a circle instead of like an up and down. That's it. So say like I asked you to do sine of 240. Well, I'm going to locate 240 degrees, and then sine on the unit circle is the y coordinate. So sine of 240 is equal to negative root 3 over 2. Done. What if I asked you for tangent of 405? Wait a minute, Mr. Kulik. I'm looking at this thing, and there's no 405 on here. What the heck do I do with that? And I'd say, you're right, 405 is not on there. But is there an angle coterminal to 405 on there? 405 minus 360 is 45. And if I look at my definition, tangent is y over x. So root 2 over 2 divided by root 2 over 2 is just 1. So I take a number and divide it by itself, I just get 1. And I'm done. Nothing more. All this is a shortcut to doing problems like cosine of 150 without having to draw a picture and label things and like grind it out. It's just this. We're looking it up and writing it down. That's all. What do you guys think? Okay. I'll have your own copy of this for you guys to use next time. I have one more example though, and then we're going to be donezo with me talking as loudly as I can manage about mathematics that you should care about more than you do. Our last example says find sine theta if cosine theta equals 5 over 7 and cotangent theta is negative. This is going to be a 3-step problem. The first thing that I want to do is figure out what quadrant the terminal side of my angle lies in. So cosine is 5 over 7. Well, that means cosine is positive. Cotangent is negative. Well, I know tangent is going to be the same because it's the reciprocal of cotangent. So tangent's also negative. So I'm going to draw my picture. And I know all silly turtles crawl. And I'm going to go, okay, where's the places where cosine is positive? Well, the A stands for all of them positive. So cosine is one of all of them. And C stands for cosine is positive. So I could be in quadrants 1 or 4. Now I'm going to look at where tangent is negative. Well, if I look here, I know tangent is positive at A for all and T for tangent. So it's negative everywhere else. What quadrant does my angle have to be in then? Quadrant 4. Where both inequalities hold. So far, so good? So I'm going to draw my picture now of my angle. And I'm going to use my point definition here. So to do that, I'm going to need to figure out what the x and the y and the r for this angle. Everybody's okay? You could do it that way, but it's much harder. Let's not. We know that cosine theta is 5 over 7. If I use the point definition and not the unit circle definition, I know cosine is also x over r. So that tells me x is 5 and r is 7. You guys happy with that? So far, so good. Now to find y, I remember that x squared plus y squared is equal to r squared. So 5 squared plus y squared is equal to 7 squared. 5 squared is 25. 7 squared is 49. If I subtract 25 from both sides, I get y squared is 24. And if I square root both sides and I reduce my radical, the square root of 24 reduces to 2 root 6. If you can't do that in your head, don't feel bad. The square root of 24 is 4 times 6. The square root of 4 is 2, so there's the 2 root 6. So I'm going to write here 2 root 6 for y. Almost. Negative. Why is the y negative? Because it's in the fourth quadrant. Very good. Yes. 100%. So that's everything I need. It asked me for sine theta, which is just y over r. So it's negative 2 root 6 over 7. And I'm done. So the 3 steps were figure out the quadrant that theta lies in, solve for x, y, and r with the given information, and then use that to plug into the appropriate formula for whatever the question's asking for. Everybody okay? Okay. So a bunch of assignment stuff now coming your way, so listen closely. This was the last section in chapter 2. We do something every chapter that we haven't done yet. What do we still need to do this chapter that we haven't done yet? The homework quiz. You should be expecting to see one of those in the not too distant future. I wouldn't worry about anything before problem 42. So the first problem set that you turned in would be the stuff that I'd expect to see problems like on the homework quiz. If you felt good on that stuff, you should be perfectly fine for the homework quiz. It should be no big deal for you. Today, we're going to work on using our point definition for sine, cosine, and tangent. That'll include problems 45 through 50 and a delta math assignment. Next class, we're going to worry about the unit circle definitions for sine, cosine, and tangent. So we're going to work on 51 to 60, and I have a worksheet for you to work on. That'll wrap up chapter 2. So the class following that will be our review day. A gift that I give to you as regular math students is that on the review day, you're allowed to make a half sheet of notes. You can write on both sides of this sheet of paper. If you turn it in on the review day, you may use that half sheet of notes on your test, provided you are here in attendance on the test day. You're not eligible to use the half sheet on a makeup, but if you're here on the test day, I will hand it back to you. You can put whatever you want on your half sheet of notes. Can be formulas, can be example problems, can be, things for you to remember, can be definitions, whatever you want. Everybody's cool? So we'll have the review day and the test next week. Should have a homework quiz relatively soon. Today, I'd like you to work on either your delta math or your numbers 45 through 50. My suggestion would be to start with the delta math because it gives you feedback as you're going. Let me show you what you'll be doing in the delta math problems. So your new assignment is Chapter 2, Delta Math 3. So the first sets of questions, you're just going to be asking where the terminal side of theta is, what quadrant. So here it says sine is positive and cosine is positive. Well, sine is positive in quadrants 1 and 2, cosine in 1 and 4. So the place where they're both positive is just quadrant 1. If you have your All Silly Turtles Crawl picture open, it's pretty easy. The next problem is the same thing, except we're involving, you could be involving the reciprocal identities also. The next one is like that last example problem we gave, but easier, because they're going to tell you the quadrant that theta's in. You don't have to figure that out for yourself. So we're just using the point definition. And because we're in quadrant 1, you know whether things should be positive or negative. The next is the same thing, except now you can get things other than quadrant 1. So again, same idea as the previous problem, the example we just did a moment ago. Same idea here, except now the things that you're finding the exact value of are going to be like, could be the reciprocal ones too. So you could get cosecants and secants and stuff in there. Doesn't really change anything. This one is like the very first example we did, where we just give you a point and ask you to find like cosine of that theta. And then the last one is the same idea, but it's going to ask you to draw the picture first of the angle. So like 3 - 4 is going all the way around to like there, it looks like. And then you'd have to figure out what cotangent of theta is. Right? But again, the point is all you need to do that. Everybody happy? You're confused? You try a couple, you'll catch on quick. If anybody else had issues with the homework and didn't get the credit they think that they should, or that I sent you an email because you sent me some email to me first about not being able to do something or whatever, and you want to talk to me, I am now open for business.